We have seen explicit formulas for both arithmetic and geometric sequences, and those explicit formulas can be used to determine any number in the sequence just by using the position number. So if I wanted to find the 100th term, I would have no problem doing that as long as I had my formula. So just a reminder, for arithmetic sequences, the explicit formula was Tn equals A1 plus D, which is the common difference, times n minus 1, and that was linear. Whereas the geometric was exponential, so the formula for that was Tn equals A1 times the common ratio r to the power of n minus 1. Now, this video is all about recursive formulas, and for a recursive formula, you can't find a number in the sequence that is very far off, like the 100th, the 200th. It would take a very long time, and that is because the formula for Tn is written in terms of the previous number, which is Tn minus 1. So I just want to show something quickly. If my current number is Tn, where n is the position number, the number after that would be Tn plus 1, because if I'm on the 10th number, then the next one would be the 11th number, which is just me adding 1. And then the one after that would be Tn plus 2. And then if I work backwards, the one before Tn would be Tn minus 1. Again, if I'm on the 10th number, the one before would be the 9th number, which is 1 less than 10. And then the number before that would be Tn minus 2. So your recursive formula for a certain number depends on the previous term. Which means if you're given the first term and you're given the recursive formula and you want to find the 200th term, you would have to apply that pattern 200 times to get to the 200th term, and that would be very tedious. So for something like that, the explicit formula is a lot better. But the recursive formula is something that is a little easier to understand what is going on with your sequence. So for this example, I have a few different sequences, and we're going to determine if the sequence is arithmetic, geometric, or neither. Then we'll figure out the recursive formula for that sequence to practice this new skill. And then if it is arithmetic or geometric, we'll do the explicit formula as well. So let's get started with our first sequence, which is 5, 11, 17, 23, 29. So I just want to check, is there a common difference or a common ratio or nothing? So if I look at from 5 to 11, I would be adding on 6. And then I check from 11 to 17, I'm still adding on 6, plus another 6 to get 23, plus another to get 29. So clearly I have a common difference of 6, which makes this arithmetic. Now, if we know it's arithmetic, let's just go ahead and find the explicit formula. And our explicit formula, Tn, is going to be the first term, which is 5, plus the common difference, which is 6, times n minus 1. So that's great. Now let's figure out this recursive formula. So we know that to go from one term to the other, we're just adding 6. So my recursive formula for Tn, I'm taking my previous number, which is Tn minus 1, and I'm adding 6 to it. And that's all it is, previous number plus 6. Now, with a recursive formula, you really have to state what the first term is, or else if someone saw this, they wouldn't know where to start. So because everything is in terms of t's here, I am going to write T1 for the first term, and our first term is 5. Now in this sequence, I did give you the first term. If I didn't, then you'd kind of have to work backwards to get that first term. Let's try another sequence. So for B, 8, negative 16, positive 32, negative 64, positive 128. So right away, I already know it's not arithmetic because I can't jump around between positive and negative so much. So I'm going to test for a common ratio. So I see to get from 8 to negative 6, I'm multiplying by negative 2. Now let's test it out. From negative 16 to 32, I am again multiplying by negative 2. 32 times negative 2 is negative 64, and negative 64 times negative 2 is positive 128. So that's great. The common ratio is negative 2, making this geometric. So the explicit formula is Tn equals the first term, which is 8, times our common ratio, all to the power of n minus 1. Now let's try the recursive. So for my recursive formula, I know to get from one number to the other, I'm just multiplying the previous term by -2. So Tn is taking the previous term and multiplying it by -2. Now, I personally don't like this layout. It works well for when I say it verbally, but I know that usually we put our coefficient out in front, so I'm just going to do -2 times Tn minus 1. So the -2 times the previous term. But either way works well. Just make sure that -2 is in brackets, or else it looks like you're subtracting 2 from Tn minus 1 instead of multiplying. And regardless of which way you write it, we have to remember to write our first term, which is 8, or else someone who saw this wouldn't know where to get started. All right, let's try the next example. So here I have 1, 1, 2, 3, 5, 8. I can clearly see I don't have a common difference because to go from 1 to 1, I'm adding 0, and I'm definitely not adding 0 to get to 2, so no common difference. Common ratio, to get from 1 to 1, I'm multiplying by 1, but 1 times 1 is not 2, so this is neither. And now there's no set rule on how to figure out what this sequence is, so you kind of have to think a little, try some things out, try to find a pattern here. So if we look at this, maybe you will notice 1 plus 1 is 2. 1 plus 2 is 3, which is the next term. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. So that would be the next number in my sequence if I wanted it. So to get the next number, you're adding the previous two numbers, which means for our recursive formulas, I don't only depend on the previous term, I depend on the one before it. And the one before it would be represented by Tn minus 1. So to get any number, I'm adding the previous number to the number that came before it. And now because I am relying on two different terms, I don't only have to state the first term, I have to state the second term as well. So T1 is 1 and T2 is 1 as well. That way, someone can actually start the sequence and write it out. 1, 1, and then they can start adding the previous two terms to go from there. And finally, our last sequence, 2, 4, 16, 256, 65,536. Clearly no common difference because I can't jump that high up. And if I try to see if there's a common ratio, 2 times 2 is 4, but 4 times 2 is 8, not 16. So once again, this is neither, and we have to use the visual and try to problem solve to see the pattern. So if I look at this, I know 4 is the same thing as 2 times 2, and 16 is the same thing as 4 times 4, which is the previous number. 256 is the same thing as 16 times 16, and so on. So I can rewrite 4 as 2 times 2, or 2 squared. I can write 16 as 4 squared. I can write 256 as 16 squared. And I can write 65,536 as 256 squared. So just looking at this visual, I can tell that for my recursive formula, it's the previous term times itself, or the previous term to the power of 2. So I can write it as Tn equals the previous term squared. Or if you really wanted to, you could just write the previous term times itself. I personally wouldn't write it like this, but either way works. And of course, we have to remember to state that T1 is 2. And that will help anyone get started on the sequence. So that's the recursive formula. The recursive formula can be easier to understand what is going on in the sequence, because some sequence, like the last two, finding an explicit formula might be very difficult to do. Yes, the explicit formula is easy to use and you can find things long term, but sometimes the explicit formula is a little harder to figure out, whereas the recursive one, if you find the pattern, you can easily put that together. But its disadvantage is that it would be a very tedious thing to find the 100th or 1000th term.